In this lecture, I'll be talking about limits, as you can read on the slide. Limits are the backbone of calculus. We always want to see what's happening as something gets really, really close to something else, or really, really small, or really, really bigger. And you'll see what I mean in a couple of slides. When we do limits, we care about what happens as you get close to something else, not what actually happens at the point. So let's show you what I mean. Suppose we've got average to a function here. Here's f of x, and I'm going to grab a point. Let's say I don't have numbers on the x. We'll call that a 5, and we'll say f of 5 is 4. So I want to know what's the limit as I get close to 5, not what actually is happening at 5. Okay, so I'll plug in something bigger than 5. If I plug in something a little bit bigger than 5, the function value will be something a little bit smaller than 4. This makes sense because your function is decreasing, so that's going to happen. If I grab another one just a little bit closer to 5, from the positive side of 5, I will get a little bit closer to 4. It looks like if I keep doing this and get closer and closer to that red dot, over here I'll get closer and closer to the 4. So I'll be able to say that the limit as x approaches 5 from the positive side of f of x is 4. I tend to say x approaches 5 from the positive side. A lot of people will say from the left or the right. I am a little dyslexic. I get my left and my right mixed up. So rather than screwing it up, I'm going to try to stick with positive and negative side. Let's try from the other side. I'm approaching 5 from the negative side. I put in something here, and it looks like I hit something bigger than 4. If I get a little bit closer to 5, then I will get a little bit closer to 4 on the y-axis. It will keep going as I keep getting closer and closer to this 5. I will keep getting closer and closer to the 4. So I can say that the limit as x approaches 5 from the negative side is also 4. Since the limit from the left and the right, ooh, look, I said left and right are the same, then we can say that the limit is equal to 4. Now, one thing to note, you might say, well, duh, Megan, look at this. I can see that it's getting closer and closer because that's where the function value is. It's nothing weird. You're right. If a function is continuous, then the limit at that point exists, and it's the value of the function. So this is a big thing to remember. If a function is continuous at x equals a, then the limit as you approach a for f of x is f of a. But what if it's not continuous? What if you have a hole? F of 5, the function value doesn't exist, but what about the limit? Well, it looks like it's still going to be 4, right? So I put in something bigger than 5, I get something less than 4. I go again and get something closer to 5, then I get closer to 4. The limit from the positive side is 4 again. If I do it from the negative side, I'll get closer and closer to 4 again. So the limit from the negative side is also 4. Since the limit from the left and the right both equal to 4, then we say the limit exists and it is 4. Since the limit of f of x as x approaches a does not equal f of a, then we say f of a is discontinuous at x equals a. There's a hole. Well, what if it's not a hole? What if it's a jump? What if there's a break? Well, let's try it again. Let's say I'm going to just call this 5. It looks like the open hole is at 4 and the closed hole is at 6, which means f of 5 would equal 6. But again, we don't care what actually happens at 5. We want to know what happens as we get closer to 5. Let's plug in numbers closer to 5 from the positive side. I'm going to get closer and closer. It sure looks like, again, I'm approaching 4. Now, if we do it from the negative side, though, well, all this stuff goes again, then I'm getting closer and closer to 6. So the limit from the negative side is 6. The limit from the left and the limit from the right are not equal, which means the limit does not exist as x approaches 5. What if you're given a function? Now, this is where we want to remember that things are continuous. Wherever they're continuous, the function will be, the limit will exist at that point. Now for this function, x plus 2 over x minus 2, the only weird point will be at x equals 2. That's the only funky point. So if x equals 3, that ain't 2, so we can just plug it in and get 5. So the limit as x approaches 3 of x plus 2 over x minus 2 is 5. Let's try this one. X minus 3 over x squared minus 9. This function is continuous everywhere except at x equal plus or minus 3. And unfortunately, we're looking at plus or minus 3. So I need to do some jiggling and factoring and figuring stuff out. So I can see that the bottom is factorable as x minus 3 times x plus 3. those guys will cancel, and that's what's giving us the zeros, and we want the zeros hopefully to cancel. So what's left is just 1 over x plus 3. The only problem with this function is at -3, we're not going to -3, so all's good. We can just plug in. Overall, what you want to try is plug in the number. If you get a normal number, that's your answer. If you get something funky, you jiggle, you factor, you cancel. Right now, funky means 0 over 0. There are other funky things, but I won't give you anything other than 0 over 0. If you get like 0 over 1, well, that's just normal 0. That's no big deal. 1 over 0, the world explodes. That's not good. Remember, plug in first. If you get a normal number, that's good. If you get something funky, you need to jiggle and play with it. For the graphic ones, just follow the function to see what y values get spit out when you plug in the x values.